We welcome you to learn about the Vanguard AI Conformable Venous Atlas. Our healthcare ecosystem is filled with silos of expertise. These non-interoperable islands of interoperability lead to volumes of low-quality data, lack of common data sets, discoordinated care, rising costs, and impediments to innovation. To build a platform-based learning health system, we must change the fundamental dynamics. The Vanguard Integrated Medical Management and Education Gateway builds on this concept, innovating to improve availability of high-quality data and to reframe the relationship between the clinician-patient team and the decision-making process. We lack high-quality data at critical decision points of care for those who need central venous access devices for life-preserving therapies. 8 million catheters are sold each year. Related complications add $20 to $60 billion a year to health costs. Loss of a catheter can mean loss of life. Loss of venous pathways is cumulative and irreversible. Many complications are attributable to elective decisions, but there is often poor feedback to decision makers. It can take hours to reconstruct a patient's venous access history. If the data even exists, it is dispersed and often unavailable when decisions are made. A large amount of critical data is missing or incorrect. A venous catheter can only be visualized with medical imaging. Conventional imaging is cheap and easily performed, but comes with challenges. On a plain X-ray, we can see certain useful reference structures, bones like the spine and ribs, and soft tissue structures like the airways. For a central venous access device, we can see its course and the catheter tip. On a plain chest X-ray, we cannot see veins or heart chambers. Most statements made by health professionals about the position of venous catheters are therefore guesses, and poorly made guesses have harmful consequences. Without the ability to see venous structures, we can't know the safest place for a catheter. We can't tell where prior catheters have been or how their location may have related to adverse outcomes. Misunderstandings delay actions that can protect health and prevent harm. A reliable venous map would allow us to find where we are and where we intend to go. It would permit us to link patients with their devices. It would permit efficient, effective, and measurable procedure planning. With a venous map, we can assess data rapidly at the critical decision points of care. The map would allow us to organize data tracking, to consolidate data in one easily accessible place, and to make reliable use of it at a glance. What used to take hours or was impossible can now be accessed reliably in seconds at the critical decision points of care. With such a tool, clinicians can recognize problems earlier and more clearly, allowing timely correction and prevention of harm. The IMEG Venous Management System AI model intentionally realizes the precepts of a platform-based learning system. Let's learn how it works. Our solution architecture has a modern, scalable, angular front end using the NGRX State Management Library integrated with a robust, secure, serverless backend built entirely on cloud-based AWS infrastructure, offering a tightly aligned, seamless, event-driven flow from user interaction to data persistence and retrieval. This architecture delivers performance, security, and interoperability. Strategically, this architecture meets the needs of common business use cases. Every component, from Lambda to DynamoDB, auto-scales with demand. This means we can support a growing user base without needing to re-architect. Security is built in at every level. Cognito provides user authentication, while identity and access management policies enforce tight control throughout. Angular CLI and serverless backend reduce boilerplate and accelerate development cycles. Pay-per-use for compute, storage, API calls keeps infrastructure costs low, especially in early-stage deployments. Elasticsearch gives users fast search and filtering, while CloudWatch provides the team with detailed real-time operational insights and alerting. All of this enables a lean, secure, and responsive solution ready to support growth and innovation. Please enjoy this fully operational demonstration of the IMEG Venous Management System running on AWS and connected in real time to the DICOM and FHIR sandboxes of the Society for Imaging Informatics in Medicine. The workflow is real, the organization's patient and imaging data are simulated. At the administrative level, an organization has created a shared registry that can capture and track each venous access patient encounter. Here we select Kaiser Permanente's registered imaging studies and view simulated patient John Smith. IVMS automatically implements security requirements like OAuth scopes, tokens, or MTLS settings and looks up Kaiser's FHIR server. Using this information, IVMS then requests the imaging study resources related to John's record. IVMS reads the endpoint details and organization metadata so it knows exactly where and how to access the right DICOM server. Using the DICOM WAITO-RS protocol, it securely retrieves the actual DICOM image for this study and sends this data to the Venous AI server, requesting automatic landmark identification. Our AI processes the image and returns precise coordinates for key anatomical landmarks. The clinician can accept the displayed AI landmarks or manually adjust them. Any adjustments are archived for future AI training and QI. IVMS then projects the Venous Atlas into the coordinate system of the patient X-ray, providing a clear anatomical reference map. Clinicians use the IVMS toolbox to create archived annotations for anatomic or clinical features, such as intended or actual catheter entry point and tip position. The annotated locations are normalized against the Atlas coordinate system and saved to the registry. Our solution uses FHIR as a metadata and routing layer, not as an image store. The solution easily orchestrates imaging workflows across multiple organizations without storing raw images. FHIR provides a clean separation between clinical and image data and allows transparent integration with heterogeneous infrastructures while staying fully standards compliant. The Venous AI server is a solution core, analyzing X-rays, detecting anatomical landmarks, and producing actionable insights that empower clinicians to diagnose faster and with greater precision. It transforms raw imaging data into clinically valuable intelligence. To create the training data, expert radiologists determined the DICOM coordinates of target structures on each sample image, using contemporaneous chest CTs for precise 3D validation. In this way, bony structures and the division of the airway, known as the carina, were identified. The venous segmental boundaries were located and marked. A selection of these landmarks defined the coordinate system and vector basis for the X-ray. We also applied randomized data augmentation techniques during training. Each original image could be transformed in several ways to simulate the variability seen in real clinical imaging. These augmentations boosted the dataset to nearly 5,000 unique variations, significantly improving the model's ability to generalize landmark locations and reduce the risk of overfitting. MONAI is the backbone of our Venous AI pipeline. Its specialized transforms handle image normalization, orientation alignment, and pre-processing, ensuring our AI models receive standardized inputs. Leveraging PyTorch and NVIDIA GPU acceleration, IVMS achieves near real-time inference, identifying key landmarks with high precision. We modified MONAI's DenseNet 121 architecture to specialize in Venous AI landmark detection for grayscale X-ray images. As a state-of-the-art convolutional neural network architecture, DenseNet's dense connectivity, where each layer directly accesses the outputs of all previous layers, promotes exceptional feature reuse, reduces the number of parameters, and leads to highly efficient training. Extensive pre-training on a massive dataset means the model has already learned rich generalized visual features, edges, textures, shapes, and object patterns that can be quickly adapted to the medical imaging domain. We added a custom regression head to the DenseNet backbone, designed specifically to output precise landmark coordinates, using dropout and batch normalization to improve generalization. This allowed efficient training on relatively small datasets with high accuracy and flexibility for different landmark configurations. In use, the AI predicted points generate vectors that determine the basis for calibration of the SVG map individualized to the patient's X-ray. The Venous AI model was trained for 420 epochs, processing approximately 5,000 training impressions during its learning cycle. On the left, we see the ground truth, the expert-curated landmarks. On the right, VAI's predictions are shown at various points in training. Early predictions are crowded and misaligned. As the epochs progress, AI outputs gradually converge toward correct positions. As it learns, the model steadily progresses to accurately identify anatomical landmarks from unknown images. Real patient needs guide development of our solution. Many systemic factors impair patient access to quality and cost-effective care. By intentionally attending to these issues, our solution will translate effectively to other large populations and disease processes, and will transform the way automated extraction of real-world healthcare data drives practices, process improvements, and cost containment. We appreciate your kind attention.